Alright, in this video lesson, we're going to focus our attention on double systems. Now, we've been doing a lot of work with Newton's second law and looking at force net acting on a system and how the net force is equal to the mass of the system times its acceleration. And we've done some simple problems. We've also done some problems on elevators. And in this video lesson, we're going to cover what's called double systems. And we're going to apply our same knowledge of Newton's second law to these situations. Before we get started with an example, let's just first talk about what a double system is defined as. A double system is defined as a system where there's more than one object. And that can mean a variety of things. The example we're going to look at right now is a picture below, and we have two boxes. We've got a blue box and we've got a yellow box. And we have some force applied from a hand pushing the two blocks from the left-hand side or from the contact with the blue. So what defines it as a double system is the fact that both the blue box and the yellow box are moving together. It's two separate objects, but they're moving together. And so since they're moving together and acting together, they are going to have the same acceleration. So a double system is defined as where it's more than one object. So let's just take a look at this example right now. A 5 kilogram and a 10 kilogram box are touching each other. A 45 Newton horizontal force is applied to the 5 kilogram box in order to accelerate both boxes across the floor. We're going to ignore friction forces, and we want to determine the acceleration of the boxes and the force acting between the boxes. Before we get started, let's go ahead and write a few notes. First of all, when you're finding the acceleration, notice how it says what is the acceleration. It doesn't specify necessarily the acceleration of the blue box or the yellow box. And that's because their accelerations are going to be the same. Okay, because think about it, if you're pushing both of those boxes across the table, they're both, since they're touching, they're both going to be accelerating at the exact same rate. So the acceleration is the same for both of them. And so when we're asked to solve for the acceleration, we're going to treat the system as one object. Okay, so when you're asked to find the acceleration, we're going to treat it as one object. Now, for the second part of the question, we're asked you to define the force acting between the boxes. So in other words, the force that the blue acts on the yellow and the yellow acts on the blue. Those are the forces in between. When you need to find those forces, we're going to go ahead and split the system into two. All right, so I'll leave that up there to remind ourselves that we're going to treat it as one system when we find the acceleration, and then separate to find the force. Okay, so let's go ahead and do this problem. I'm going to go ahead and minimize this a little bit so we can get some more space here. I'm going to bring this up here. Okay, so the first question is determine the acceleration. Okay, so we're going to treat this whole thing, even though it's two separate boxes, we're going to treat it as one thing. So it's almost like, okay, if this is 5 kilograms and this is 10 kilograms, it's almost like, let's pretend for just a moment that we were just pushing one box with a mass of 15 kilograms. Okay, and then that's me in my hand pushing it to the right. Okay, so that's pretty simple. We can do that. So if we draw a force diagram, we know that force gravity points down, and that's 150 newtons. We know force normal is going to point up, and that's also 150 newtons. Excuse me, I'm kind of going into the words a little bit. And then we're told that the force applied is going to go to the right, and that's 45 newtons. And then that's it, because we don't have any friction in this problem, so we're ignoring friction. So we need to find the acceleration. Okay, so acceleration for an object that is not in equilibrium is going to be coming from Newton's second law, which is force net equals mass times acceleration. When I ask you what force or forces are contributing to the net force in this problem, the only force that's contributing to the net force is the force applied. Okay, because the normal and the gravity are going to cancel each other out. So really the only force that goes into the net is the force applied. And then that's going to be equal to mass times acceleration. Okay, so the force applied we know is 45 newtons. And that's equal to the mass of the entire system. We're treating it as one thing. So the mass is 15 kilograms. And then that's equal to A. And so we solve for A, and acceleration would be 3 meters per second squared. Okay, so now remember, even though that's the acceleration for the entire system, that's also the acceleration for each individual box, because they're both going to be moving at the same rate. Now what we're going to do is we're going to go ahead and solve for what is the force tension or force applied. Excuse me, for the force between the box. So let me get myself a little more space here. Okay, so now that was the first part of the problem. I now need to solve for what is the force acting between the two blocks. Now, since this is the first time I'm showing this, I'm going to actually show how you can solve this using both boxes, but then from here on out, I'll only choose one. So now, since we're solving force, we're going to split into two. So we need to treat the 5 kilogram block and the 10 kilogram block separately. Okay, and actually I'm going to move this to the side so I can conserve some space here. Okay, so if I drew the force diagram for the 5 kilogram block, what forces are acting on it? Well, I have force gravity going down. I've got force normal going up. I've got the force that the hand is pushing on it, so we'll call that force applied. And then I've got the force of the 10 kilogram block pushing back on it. So I'm going to actually just call that F sub 10. So we know that that's the force that the 10 kilogram block is pushing back on it. Now, if I draw the force diagram for my 10 kilogram block, I'm going to have force gravity down. I'm going to have force normal up. And then I only have the force that the 5 kilogram block pushes. Notice that the 10 kilogram block does not have the force applied because the hand is not touching the 10 kilogram block, it's touching the 5 kilogram block. So there's my force diagrams. Now, I'm going to, like I said, show you how you can solve this problem using both blocks, but you don't need to do both. You only have to choose one block and find the force. Okay, now before I do that, I want to make sure we understand this conceptually. Okay, remember how I drew up at the very top here that the 5 kilogram block is pushing to the right and the 10 kilogram block is pushing to the left, right? Those forces right there are what we call action-reaction pairs. We learned that when we learned about Newton's third law. Newton's third law states that for every force, there's an equal and opposite force. So if the 5 kilogram block pushes on the 10 kilogram block pushes on the 5, and those forces are equal in magnitude, but opposite in direction. So what does that mean when I look at the force diagrams? What that means is the magnitude of this force is equal to the magnitude of this force. Okay, because the force on the left, this is the force that the 10 kilogram block pushes on the 5, and this is the force that the 5 kilogram block pushes on the 10. We know due to Newton's third law that those must be equal. So that's why we only have to solve for one block to solve for the answer of what's the force in between. So let's go ahead and do that now. All right, I'm going to go ahead and choose the 5 kilogram block for the first time around. So we have force net equals mass times acceleration. Now, looking at the 5 kilogram force diagram, what force or forces are contributing to the net force? Well, you've got the force of the 10 kilogram block plus the force applied, and then that's equal to mass times acceleration. Okay, now we're going to go ahead and plug in numbers. Now, when you go to plug in numbers, it's very important that you know which direction you're making positive. And actually, I should have made that at the beginning, but I forgot to. But let's do that now before we make a mistake. So, do you want to make left positive or right positive? Typically, what we do is we like to make the direction that motion's happening the positive direction. So what that means is any vector that's pointing to the right is going to be positive, and any vector that's pointing to the left will be negative. So the reason why that's important is when I start to plug in numbers for my forces here, I need to keep that in mind. So force 10, okay, the force that the 10 kilogram block pushes on the 5, that's actually what we're solving for. So I'm going to leave that force sub 10, plus my force applied. Now my force applied is 45 newtons. Is that a positive 45 or negative 45? Since the positive 45 is pushing to the right, and I've made right my positive direction, it's a positive 45 here in the equation. That's equal to mass, now be careful here, it's just the mass of the 5 kilogram block, times its acceleration. We know the acceleration is 3, and since it's accelerating to the right, that's a positive 3. Now I'm going to go ahead and solve. F sub 10 plus 45 is equal to 5 times 3 is 15. I'm going to subtract 45 from both sides. Okay, and notice that I get the force that the 10 kilogram block is pushing on the 5 is negative 30 newtons. And we know that it should be negative because remember, the force that the 10 kilogram block pushes back is in the negative direction. So that actually makes sense that we should get a negative. But the force is 30 newtons. Now what I'm going to do is I'm going to go ahead and solve this problem now using the 10 kilogram block so we can understand that it's the same thing. To clean some things up, I'm going to go ahead and erase this side right here so we can have some more space. Okay, so we're done with the 5 kilogram. We're not going to worry about that anymore. I want to leave that 10 kilogram one up there. So now I'm going to do the exact same thing using the 10 kilogram block. So force net equals mass times acceleration. What force or forces are contributing to the net force with the 10 kilogram block? Well, in that case, it's just the force that the 5 kilogram block pushes. So my force net is really just F sub 5, since the normal and the gravity cancel out. So that's equal to the mass times the acceleration. Now, my F5 is what I'm solving for, and that's equal to the mass, which is, what mass are we looking at now? It's 10 kilograms times the acceleration. And acceleration for the 10 kilogram block is also in the positive direction, so it's 3 meters per second squared. Force 5 equals 10 times 3 is 30, and we're now in units of newtons. And notice we got the exact same answer. Notice that here it's positive because according to the 10 kilogram force diagram, that force is pointing in the right direction. So no matter which block you choose, you're going to get the same magnitude of 30. You will just get opposite signs because they'll be pointing in opposite directions. All right, let's just do one more example so we can keep this video kind of short. All right, notice in this example right here, we are looking at the same exact situation, only now we're adding friction. So a 5 kilogram and 10 kilogram box are touching each other just like before. A 45 Newton horizontal force is applied to the 5 kilogram box in order to accelerate both boxes across the floor. Now the coefficient of friction we're told is 0.200. Once again, determine the acceleration and the contact forces. Okay, so remember, to find the acceleration, we're going to treat it as one system. So if we think about this as one system, we've got the force of gravity down. And force of gravity, remember, this is 5, this is 10. So my force of gravity is coming from a 15 kilogram mass, or 150 newtons. The force normal pushing up on the blocks would be 150 newtons. Remember, I'm treating it as one system. 45 newtons are acting to the right, and now we've got a force of friction, and I actually need to figure out what is that frictional force. Remember, friction can be found by taking your mu times your force normal. My mu, we are told, is 0.2, and my normal force, when I'm treating the whole thing as one system, is 150 newtons. If I take 150 times 0.2, my force friction is equal to 30 newtons. So that's what I'm going to plug right here in the force diagram. So when I think about what is my net force that's acting on the system as a whole, my net force is going to come from my force applied plus my force friction now, equaling mass times acceleration. The force applied we know is 45 newtons, okay, and it's positive 45 because I'm making right the positive direction. So then plus my friction's 30, but it's negative 30 because friction points in the negative direction to the left. And that's equal to the mass of 15 kilograms times A. If I clean that up a little bit, 45 plus a negative 30 gives me 15 newtons. That's equal to 15 kilograms times A. So acceleration would be 1 meter per second squared. And that makes sense because before, when it was no friction, it was 3. So it makes sense that it's less acceleration when there's friction. So that was the first problem, which is solving for the acceleration. Now I'm going to solve for the second part. I'm going to solve for the force between, or the contact forces. Now remember, you only have to choose one block at this point. Choose whichever block you want. What I do is I typically choose the block that's going to have less forces acting on it. And in that case, it's the 10 kilogram block, because the 10 kilogram block does not have the hand touching it. So I know that I'm going to have less forces. So if I draw the force diagram for the 10 kilogram block, I have force gravity down. Be careful now, you're dealing with just the 10 kilogram block. So it's 100 newtons of gravity, which means it's 100 newtons of normal. The force that the 5 kilogram block pushes on it is to the right. And then there is friction with the 10 kilogram block since it's got a coefficient of kinetic friction there. Be careful, don't put 30 here. 30 was the friction when you were treating it as one thing. Now we're just looking at the friction just acting on the 10 kilogram block. So we need to figure out what's the frictional force acting on just the 10 kilograms. We're going to find out the same way. The mu, which is 0.2, times the force normal. The force normal now is 100. So what's my force of my force friction? It's 20 newtons, not 30. So now I'm going to use my Newton's second law. Force net equals mass times acceleration. My force net comes from two forces. My force from the 5 kilogram block plus the force of friction. That equals mass times acceleration. My force sub 5 is what I'm solving for. Plus, my friction is 20, but it's a negative 20 because it's pointing in the left direction. Left is negative. Equals the mass, which is 10 kilograms, times the acceleration is 1. Is it a positive 1 or negative 1? Well, since the object is accelerating to the right, that's positive. And so if I clean that up a little bit, f sub 5 equals f sub 5 minus 20 equals 10 times 1 is just 10. And if I solve for f5 by adding 20 to both sides, I end up getting that f sub 5 is equal to 30 newtons. And isn't that interesting? The contact force is still the same even though there's friction, because the friction is only going to affect the acceleration, but the actual forces that those two blocks are touching on each other is still the same. What I'd like to do now is I'd like to give you two more problems, but I don't want to work them out. What I'm going to do is I'm going to pause the video and allow you to do that, and then you're going to hit play when you want to reveal the answer. Okay, take a moment and look at the answers. I try to keep them separated, steps 1 and 2. The first thing I want to notice, in case you did, is on the left side of the screen here, I designated the up, the positive direction. And that just makes sense because if the elevator is moving up, everything's happening up. So it just makes it easier. So for number 1, the net force, if you take into consideration the 166 up and the gravity of the whole system down, your net force is 26 newtons. Divided by the mass of the whole system gives you the acceleration of 1.86. Now, when I solve the force in between, I'm going to choose the block that has less forces acting on it, and that would be the 6 kilogram, since the 8 kilogram would also have the force of the floor on it. So I'm going to choose the 6. So the 6 kilogram block has the force from block 8 pushing it up, and the 60 newtons of its own gravity pushing it down. Over here, I set force net equals to mass times acceleration. Two forces that make up your net force is the force from F8 and the force of Fg. I plug in my values. Notice that my gravity is negative because the gravity is pointing down and up is positive. My acceleration is positive, however, because the block is accelerating up, so it needs to be a positive value. And that gives you the force of 71.16 newtons. Now, if you use the other block, you probably got something a little bit off, maybe like 71.12 or something like that. That's fine. That's just due to rounding. So let's give you one more problem. All right, last practice problem right here. I want you to go ahead, let me get my screen out of the way there. I want you to go ahead and read this problem, so pause the video, read it, and then hit play to resume. Okay, so go ahead and take a look at the solutions here. For number 1, for finding acceleration, I treated the system as a whole, so gravity and normal is 100 newtons. The force applied to the right is 25 newtons, and then since there's friction here, I need to take that into consideration. I have friction solved for over here as the total system. Friction is found by taking the mu, which is 0.12, times the normal, which for the whole system is 100. That gives me 12 newtons of frictional force. So then over here to the right, when I solve for my acceleration, my force net comes from two forces, the applied in the right direction and the friction in the left direction. Notice how applied is positive 25. The friction is negative 12 because it's in the opposite direction. Divided by 10 kilograms gives me the acceleration of 1.3 meters per second squared. Then when I want to solve for the force tension, I need to just pick one of the blocks. I chose the 3 since it'll have the less forces acting on it. So I've got the force diagram for the 3 kilogram block. I have the 30 newtons of gravity and normal. Force tension goes to the right, that's what I'm going to solve for. And then frictional force is opposing. Notice the frictional force is now 3.6 because I have to solve for friction for just the 3 kilogram block. And that was done down here. 0.12 times the normal for the 3 kilograms, which is 30, gives me 3.6 newtons of resistive force. So when I go to do my Newton's second law here, I have the net force as a combination of the tension plus the friction. So that's tension, which is what I'm solving for, plus a negative 3.6 because the left direction is negative. That's equal to the mass, which is 3 kilograms times its acceleration. And I get 7.5 newtons as the tension force. This concludes the video on the introduction to double systems.